Each radioisotope has a unique rate of decay, its half-life, T sub 1/2, which is the time required for half of a sample of a radioisotope to decay into something else. An isotope's half-life is independent of temperature, pressure, and its state of chemical combination. This is actually a remarkable fact, I think. If we have a radioactive sample and we heat it up, it doesn't change the rate at which it decays. If we cool it down, it doesn't change the rate. If we increase the pressure, decrease the pressure, react it with fluorine, it doesn't matter. The half-life of a given radioisotope will not change. There's nothing we can do. One purpose of transmutation technology is to minimize risk to humans and the environment by changing nuclides with very long half-lives into ones with shorter half-lives. If we use this transmutation technology to change isotopes with long half-lives into ones with shorter half-lives, such that the radiation will have diminished to a greater degree in a shorter amount of time, that's really the only thing we can do. If we don't do that, we just have to wait. Radioactive decay is a first-order kinetic process. Recall the first-order rate law, which looks like that. You might have seen this if you have studied chemical kinetics, where the K was called the rate constant. Here, it's the same equation, but we call K the decay constant. And the N's are amounts of radioisotope. Could be number of grams, could be number of moles, it really doesn't matter. In units on chemical kinetics, the N's were often written as concentration of a reactant, or for a gaseous reaction, partial pressure of reactants. You might have seen that equation before, and you might have seen the first order equation for half-life, which looks like that. K times the half-life is equal to 0.693. Let's derive the first order equation for half-life from the first order rate law, which is right there. By definition, after the half-life T1/2 has elapsed, this is what we have. We have only half of what we started with. Let's say we start with 1. After the half-life, by definition, we don't have 1 anymore. We only have half. And, by definition, after the half-life has elapsed, the time that has elapsed is right there, the half-life. The left side of this equation is simply a number. It's the natural log of 2, which is equal to 0.693 something something something. And therefore, that's where you get the first order equation for half-life. KT 0.693. KT 0.693. KT 0.693. Right, stop that. Silly person. So let's try an example. Molybdenum-99 has a half-life of 67 hours. How much of a 1 milligram sample of molybdenum-99 is left after 16 days? First, because we have hours and we have days, that's not going to work, so I'm going to convert 16 days into hours. Then, since we know the half-life, we can figure out the decay constant. And there it is. I've left plenty of significant figures there. K does have a unit. It is a time unit to the -1st power. So here it's hours to the -1. Then we're going to use the first order rate law, and we're going to say, well, the initial amount of molybdenum-99 that we started with is 1 milligram, and the question is, how much do we have after 384 hours have passed? There's our decay constant. I'm not going to show the work for solving this, but hopefully you can do that. You would do something like take e to the both sides to get rid of the natural log, and then you would do a little algebraic manipulation to solve for n sub t, You should check it out on your own. I got 0.0188 milligrams. Now, what does that represent? That represents the amount of molybdenum 99 that we still have. The rest, in other words, 0.9812 milligrams, is not molybdenum 99 anymore. It's something different. Maybe it's stable, maybe it's radioactive. We don't have enough information to tell. But only 0.0188 milligrams are still molybdenum 99. Let's summarize rates of radioactive decay. For a given radionuclide, its half-life is independent of temperature, external pressure, and its state of chemical combination. Aside from transmuting atoms into other types of atoms, i.e. using transmutation technology, there's nothing else we can do to alter a nuclide's rate of decay except wait. Rates of radioactive decay conform to the first-order rate law that most AP chemistry students met for the first time in units on chemical kinetics. And there they are. On the left, the first-order rate law, and on the right, the half-life equation.